Hello students, in the last lecture we discussed about ionic equilibrium, question based on ionic equilibrium. We took different solutions, solution of acid, solution of bases and solution of salt. Then we also looked at the when we titrate weak acid with a strong base, and then we tried to see how to calculate pH of the solution, how to calculate pH of the solution. So, suppose we start titration of weak acids such as acetic acid and acetic acid with sodium hydroxide with the addition of sodium hydroxide. There will be different kind of species in the solution, and based on the species in the solution we will use different concepts to calculate your pH of the solution. So, for example, if we are starting with acetic acid, 50 ml of 0.1 molar acetic acid, 0.1 molar acetic acid, and started titrating with 0.1 molar NaOH. When there is 0 ml of NaOH, in solution we have weak acid, acid which is weak, and so we will utilize the relationship that H plus ion is equal to root under Ka into C acid. When we add suppose 10 ml of NaOH, in the solution we have salt which is formed by the reaction between acetic acid and NaOH, and you have weak acid in the solution, and this solution is called buffer solution. Buffer solution, and I showed you in the last lecture how to calculate pH of this solution. pH is equal to pKa plus log salt by acid. At the equivalence point, we have only salt. So, if I add 50 ml of 0.1 molar NaOH to 50 milliliter of 0.1 molar acetic acid, we have only salt left. So, you will get 100 ml of, or you will get salt. The concentration will be number of millimole of salt formed divided by total volume, and that is your number of millimole is. So, what you have done is you have added 5 millimole of NaOH to 5 millimole of acetic acid. It means you will get 5 millimole of salt, and volume is equal to 50 plus 50. So, 100 ml. So, you have 0.05 mole per liter. So, this is your concentration. So, 5 millimole you have this thing, 5 millimole of salt has been formed, and you have 100 ml of solution, So, you see here what we have done here multiplication. So, millimole is equal to volume in milliliter multiplied by molarity, and so if I want to calculate, molarity is equal to number of millimole divided by volume in ml. So, this is the way you can calculate your concentration of the solution. Similarly, we can do titration of weak base with a strong acid, when no acid is, for example, ammonia solution with HCl. So, the ammonia solution is weak base and HCl is a strong acid. When no acid is added, you can calculate OH minus ion is equal to Kb into concentration of base. When we add HCl before equivalence point, you will get a buffer, and in this case POH will be given by pKb plus log salt by base. At the equivalence point, we have salt of weak base with a strong acid. So, you can calculate H plus ion concentration is equal to Kh, which is hydrolysis constant, into C of weak base, C of salt, and Kh in this case will be given by Kw by Kb into salt concentration. And finally, after the equivalence point, you have salt plus a strong acid, but most of the H plus ion will come from the strong acid, and so pH will be minus log H plus from acid, or concentration of H plus from acid, H plus concentration from acid. So, this is all about titration. So, if you start with a weak acid and started treating with NOH, started titration with NOH, and how to calculate pH, and similarly if you start with a weak base and started titrating with a strong acid, what should be the pH of the solution. So, once you understand the concept, it is quite easy to calculate pH of the solution. Next application of ionic equilibrium is calculating solubility of a sparingly soluble salt. A sparingly soluble salt. So, salts are of three types. One is your soluble, but which are non-electrolyte. Non-electrolyte does not break into the solution. You have soluble salt which breaks in water, complete dissociation. here there is complete dissociation. For example, NaCl, there will be complete dissociation in water, it will be Na plus Cl minus aqueous. And last one is sparingly soluble salt. And here we need to apply concept of solubility. How much soluble this is, and this is very important from point of view of ionic equilibria. So, sparingly soluble salt, sparingly soluble salt. So, lot of salts are sparingly soluble. Sparingly soluble. What does that mean is, if we take water and if we have salt like this is positive charge, this is negative charge. If I add in water, what we are going to get is initially a small amount will get solubilized, but on addition more salt, it will start precipitating. So, very small amount of salt will be in solution. Salt will be in solution. One of the example of sparingly soluble salt is AgCl. When you put into water, it will break into Ag plus aqueous plus chloride ion aqueous. So, this is your sparingly soluble salt. Both undissociated species and dissociated species are in equilibrium, So, we can apply the concept of ionic equilibrium. We can apply concept of ionic equilibrium. So, AgCl solid is in equilibria with Ag plus aqueous plus Cl minus aqueous. If suppose solubility of salt is X, then it will give you AgCl, Ag plus aqueous. So, when it breaks, it will give you S mole per liter of Ag plus, or X, sorry, this is S, then S mole per liter, means it will give S mole per liter of Ag plus and S mole per liter of chloride ion. Now, since we can apply the concept of ionic equilibrium for these salts, so your equilibrium constant will be Ag plus aqueous into Cl minus aqueous, concentration of Ag plus aqueous into Cl minus aqueous divided by AgCl solid. And by convention we take the concentration of AgCl is equal to 1, and so K is equal to Ag plus into Cl minus, and this K is known as solubility product. This Ksp is called solubility product. Solubility product. So, there is a relationship between solubility and solubility product. Let us again understand solubility. Solubility means, suppose if I have taken AgCl, Ag plus Cl minus ion aqueous. So, how much amount of AgCl has gone to solution? So, suppose S mole per liter of AgCl goes to solution, that means that S solubility is S mole per liter, and then Ag plus concentration ion will be S mole per liter, and Cl minus concentration will be S mole per liter. S mole per liter. So, ionic product or solubility product will be your Ag plus ion into Cl minus ion, Ag plus ion into Cl minus ion, and then your Ag plus ion into Cl minus ion, and this is S into S is equal to S square. So, solubility. So, this is the relationship between Ksp and solubility. Ksp is equal to S square. So, suppose I want to know solubility, I can just take a square root of Ksp, and that will give you solubility of the salt, solubility of the salt. So, let us do some questions. So, for example, solubility of A2X3 is Y mole per liter. So, what should be its solubility product? So, A2X3 when you put into the solution, what you are going to get is 2A 3 plus 3x 2 minus 3x 2 minus, and you can see that now total charge on A is 2 into 3 plus, and y is 3 into 2 minus 6. So, this is 6 plus 6 minus, so total should be neutral. Okay. So, if suppose S is the solubility, here y is the solubility, and what you are going to get is 2y of A3 plus and 3 y of x2 minus, and we know that Ksp is equal to A3 plus square into x2 minus concentration of x2 minus cubic. So, A3 plus, this is the ion, a square, stoichiometry is 2. So, this will be a square, here stoichiometry is 3, and so there will be Q. What is the A3 plus ion concentration? This is 2y. So, 2y square into concentration x2 minus is 3y. So, 4y square into this will be Q. Yeah. So, 3 into 3 into 3 is 27, 9 3 are 27 into yq. So, 47. So, this is 108 y5. So, this is the way you calculate solubility. You can come across different salts like AB, it goes to A plus plus B minus aqueous. This is solid, and in this case Ksp will be your S into S is equal to S square. For Ab2 type of salt, you have A2 plus plus 2B minus, and so if solubility is S, you are going to get S mole per liter of A2 plus and 2S mole per liter of B minus. So, solubility will be your Ksp will be S power 1, stoichiometry is 1, 2S power 2, stoichiometry is 2. So, this is your S into 4S square is equal to 4S cube. So, it is quite easy to get a relationship between your Ksp and solubility product. So, if you know solubility, you can calculate solubility product, and if you know solubility product, you can calculate solubility. Now, similar kind of question for a sparingly soluble salt ApBq, the relationship of solubility product and its solubility is. So, ApBq, ApBq, if this dissociates, P mole of A with charge Q plus, you will get, plus Q mole of B with charge P plus, Q mole of B, sorry, this is Q mole of B charge, your charge P plus. Now, you see the total P minus. So, total charge is PQ and this is PQ. So, this is plus PQ, this is minus PQ, this will be 0, and if solubility is S, so what we are going to get is PS and this is QS mole per liter. So, you have PS mole per liter of AQ plus and QS mole per liter of BP minus. So, if I want to get solubility product which is now notation LS, so LS will be your AQ plus power, stoichiometry is P, into BP minus, stoichiometry is your Q. So, PS power P, and so this is PS, PS is the concentration. So, PS power P and QS is equal to this QS power Q. So, you have PP, QQ and S P plus Q, PP, QQ and your this thing is SP plus Q. Now, let us take another. Here solubility is given and you have to calculate Ksp, Mx4, again Mx4. So, it will break and give you M plus 4 aqueous plus 4 x minus 4x minus. So, if solubility of molar solubility of salt is S, then you are going to get S and then 4S at equilibrium, 4S at equilibrium. So, your Ksp will be S power, or you simply write M4 plus into x minus 4. So, this is S into 4S4 is equal to 4 into 4, 16 into 4, 64 into 4 into S power 5. So, 64 into 4 is equal to 6, 256. So, 256 S5. So, if you understand the concept of solubility, how solubility, you will be able to tell how much ions are formed and with the concept, with the understanding of concept of ionic equilibrium, we will be able to get Ksp for the salt. So, this is very simple example. Here solubility is given. So, suppose this is calcium sulphate, this breaks to give you calcium 2 plus sulphate 2 minus, sulphate 2 minus, and solubility is given. So, solubility, if solubility is S, then you will write SS, and here S is equal to 4.9 into 10 to the power minus 3 mole per liter at 298 K. So, Ksp will be simply S into S, that is S square, and that will be your 4.9 into 10 to the power minus 3 S square. So, it is quite simple to calculate solubility product if solubility is known. Now, see this question, solubility product of a salt having general formula this is given. Now, in this case solubility product is given, and what you need to do is you need to calculate the concentration of ion in aqueous solution of the salt. So, again Mx2, if this breaks, M2 plus 2x minus, and so if solubility is S, then Ksp will be S, this will be 2s. So, S into 2s square, and this is S into 4s square 4sq, and you have been given 4sq is equal, Ksp is equal to 4 into 10 to the power minus 12, and this is equal to 4 into sq, 4 cancels out. So, S will be 10 to the power 1 into 10 to the power minus 4. So, solubility can be calculated if we know solubility product, and concentration of M2 plus is S. So, that is equal to 1 into 10 to the power minus 4, whereas if you want to calculate concentration of X minus, then it will be 2S, means 2 into 10 to the power minus 4. Now, once you understand solubility and solubility product, we can also see what are the things which can affect solubility, and most common one is your common ion effect. So, what does that mean is that if suppose we have salt Mx solid going to M plus aqueous plus X minus aqueous, X minus aqueous. So, if I add common ion, what are the common ions? M plus or X minus. So, if we add one of them, we know that it equilibrium will shift towards left hand side. So, we are basically decreasing the solubility. We are basically decreasing the solubility. For example, if suppose we start with AgCl, which is a sparingly soluble salt, a sparingly soluble salt, it breaks into Ag plus aqueous plus Cl minus aqueous. This is solid form. So, suppose if I add Ag plus ion or Cl minus ion, the equilibrium will shift toward this and solubility will decrease. Solubility will decrease. So, for example, if I add AgNO3, this is a soluble salt. When I put into water, this gives you Ag plus plus NO3 minus. So, if you have AgCl and if you add AgNO3, AgNO3 will give silver plus ion, and this will show effect on this equilibria, and Ag the solubility of AgCl will decrease. So, let us see one question. The Ksp of Ag2CrO4 is 1.1 into 10 to the power minus 12 at 298 K, at 298 K. So, this is your sparingly soluble salt, and Ksp will be given by. So, let us see Ag2CrO4. If this breaks, it will give you 2 Ag plus CrO4 2 minus. So, if we write Ksp, this is simply your Ag2 plus A square, sorry, Ag plus A square, Ag plus A square and CrO4 2 minus, CrO4 2 minus, CrO4 2 minus. So, if suppose if we do not have AgNO3 solution, then we have simply we can just write solubility is S, then Ag plus ion concentration will be 2S, CrO4 concentration will be S, then it is simply 2S square into S 4SQ, 4SQ, and that is around 4SQ will be equal to 1.1 into 10 to the power minus 12, 1.1 into 10 to the power minus 12. But if suppose we have AgNO3, then what will happen? So, Ag2CrO4, Ag 2 Ag plus CrO4 2 minus. AgNO3 we added 0.1 molar AgNO3, it will give you Ag plus NO3 minus, and this is since this will completely dissociate. So, concentration will be, if we start with 0.1 molar AgNO3, we will get 0.1 molar Ag plus and 0.1 molar AgNO3. Now, this Ag plus will affect this equilibrium, and now if suppose solubility of Ag2CrO4 is Y. So, suppose this is Y, solubility is Y mole per liter in presence of Y mole per liter in presence of AgNO3, then you will get 2 Y here, Y, and your Ag plus concentration will be equal to 0.1 from AgNO3, 0.1 molar from AgNO3 and 2 Y mole per liter from your Ag2CrO4, and this will be Y. But we know that since this is a sparingly soluble salt, Ag plus obtained will be very less, and so this is simply equal to 0.1, simply equal to 0.1, and Ksp for your Ag2CrO4 will be, Ksp for Ag2CrO4 will be Ag plus A square into CrO4 2 minus, and Ksp we know, Ksp is given your 1.1 into 10 to the power minus 12 and should be equal to Ag plus A square is your 0.1 A square, because all Ag plus, almost all Ag plus has come from the salt, and then this is the solubility of the Ag2CrO4 in presence of AgNO3. If solubility is Y, then CrO4 2 minus concentration will be Y, and so Y is equal to your 1.1 into 10 to the power minus 12 divided by 1.1, sorry, divided by 0.1 square, and this is almost equal to 1.1 into 10 to the power minus 10 mole per liter. Now, if you remember that solubility of Ag2CrO4 was this 1.1 into 10 to the power minus 12. So, SQ will be around 0.25 into 10 to the power minus 12, and so S will be around your 1 point, so 0.1 to something like that, 0.1 or 0.15 into 10 to the power minus 4 is around 0.15 into 10 minus 4 or minus 5. So, but you can see that solubility of Ag2CrO4 in water is quite greater than your the solubility in presence of AgNO3, solubility in presence of AgNO3. So, solubility decreases in presence of AgNO3, and that is because of common ion effect, that is because of common ion effect. So, let us discuss ionic product of salt and solubility product. And this we will do for sparingly soluble salt. For example, AgCl. So, suppose you start dissolving AgCl into water. So, this is your water and you start putting AgCl. So, initially all AgCl will be go to solution and you have something like Ag plus into Cl minus. So, till all AgCl is going to solution, the multiplication of Ag plus into Cl minus ion concentration will give you ionic product, ionic K salt, or you can say this is ionic product. Ionic product. But when you add AgCl more of AgCl, when you add more of AgCl, what will happen is your solution will first become saturated. First becomes saturated. At this condition, there will be equilibrium between AgCl solid and Ag plus Cl minus in solution. So, multiplication of this Ag plus ion into Cl minus ion in a saturated solution is called solubility product. Solubility product. Solubility product. Application of the concept of solubility product. Solubility product. So, solubility product, concept of solubility product product can be used to know under what condition precipitate precipitate will form. Under what condition a precipitate will form? So, when ionic product is less than solubility product, then your solution is not saturated. Solution is not saturated. When ionic product is equal to solubility product, then your solution is saturated, and further addition of salt will lead to precipitation. When ionic product is, last one is when ionic product is greater than your solubility product. And that means your solution is oversaturated. So, based on that, we can also look at this question. It is given solid barium nitrate is gradually dissolved in a this molar Na2CO3 solution. At what concentration of barium 2 plus will the precipitate begin to form? Okay. Ksp of barium carbonate is given, that is 5.1 into 10 to the power minus 9. 5.1 into 10 to the power minus 9. So, let us see Na2CO3 gives you, when you break it, it gives you 2Na plus CO3 2 minus. And when we add Na2CO3 solution to barium nitrate, a sparingly soluble salt, barium carbonate, which is sparingly soluble, and that will form. And so, since this is sparingly soluble, barium carbonate will be in equilibrium with barium 2 plus and carbonate ion. So, now question is, at what concentration of barium 2 plus the precipitate will start to form. So, barium 2 plus barium carbonate will start to form when Ksp of barium carbonate is equal to barium 2 plus into carbonate ion. Okay. And your carbonate ion is coming from Na2CO3, and so its concentration will be equal to concentration of Na2CO3, because Na2CO3 is completely dissociated, and the concentration of carbonate, your sodium carbonate, is 1 into 10 to the power minus 4 molar. So, your concentration of carbonate ion will also be 1 into 10 to the power minus 4 molar, and then We know that Ksp is equal to 5.1 into 10 to the power minus 9, and this should be equal to barium 2 plus ion multiplied by carbonate ion. And so, since we know carbonate ion and we need to calculate barium 2 plus, so barium 2 plus will be 5.1 into 10 to the power minus 9 divided by 1 into 10 to the power minus 4. Okay, barium 2 plus ion is Ksp divided by carbonate ion concentration. So, you just divide 5.1 into 10 to the power minus 9 divided by 1 into 10 to the power minus 4, and that is equal to around 5.1 into 10 to the power is equal to this 5.1 into 10 to the power minus 5, and this is mole per liter or molar. So, after this till this point there is no precipitation, but after this precipitate formation will begin. Next question is, at 25 degree Celsius the solubility product of MgOH2 is 1.1 into 10 to the power minus 11. At which pH will Mg2 plus ions start precipitating in form of MgOH2 from a solution of 0.01 molar Mg2 plus ion. So, question is, suppose Mg2 plus ion is there and you started adding OH minus ion, at what pH your Mg2 plus ion will precipitate out. So, pH you are changing, pH is going from acidic to alkaline. So, OH minus ion is increasing, and you have to tell at what OH minus ion concentration you are going to get precipitate, at what OH minus ion concentration you are going to get precipitate, and since you know OH ion concentration, you will be able to tell at what pH precipitation will begin, at what pH precipitation will begin. So, for precipitation to begin, Ksp should be equal to Kw, or Ksp is equal to Mg2 plus ion concentration into OH minus square, and Ksp is given 1.1 into 10 to the power minus 11 is equal to Mg2 plus into OH minus ion square. So, you can calculate OH minus ion square, and this is 1.1 into 10 to the power minus 11 divided by 0.001, and this is 10 to the power minus 3. So, you have 1.1 into 10 to the power minus 8. So, OH concentration will be, OH minus ion concentration will be around 1 into 10 to the power minus 4. So, POH will be your 4, and so pH will be 10. So, at this pH your Mg2 plus ion will start. So, at pH 10 your Mg2 plus ion will start to precipitate. Since at that point Mg2 plus ion Ksp will be equal to Kw, and if we Kw go up in pH, then Kw will be greater than Ksp and precipitation will begin. Next question is, calculate the molar solubility of MgOH2 in 1 molar NH4Cl. Ksp of MgOH2 is given, and that is your 1.8 into 10 to the power minus 11, whereas Kb of ammonia is given, which is 1.8 into 10 to the power minus 5. We need to calculate MgOS2 in solubility of MgOS2 in 1 molar ammonium chloride solution. So, ammonium chloride is soluble salt, and that will give you ammonium plus your chloride ion. If we started with 1 molar ammonium chloride, we will get 1 molar ammonium plus ion, since this is a soluble salt and there will be a complete dissociation. And NH4 plus, and this will react with OH minus ion to give you ammonia plus your water, ammonia plus water. This OH minus ion will come from MgOS2. So, we have salty MgOS2, and that gives you, this is sparingly soluble salt. So, that will give you Mg2 plus OH minus ion, twice OH minus ion. This OH minus ion is utilized, and that is getting utilized with the reaction with ammonium plus ion, and that is going to give you ammonia plus water. So, this is your solubility equilibrium, and this is your opposite of your this reaction, ammonia plus water giving you ammonium plus ion plus OH minus ion. We know equilibrium constant of this, that is given. So, Kb is given, and this is 1.8 into 10 to the power minus 5. So, basically you also know K of this reaction, this is nothing but 1 by Kb. So, suppose S is the solubility of MgOS2 in 1 molar ammonium chloride solution. Then MgOS2, Mg2 plus 2 OH minus ion. So, if this is S, then this will be 2S. This OH minus ion is used up in this reaction, ammonium plus OH minus ion. So, initially you have 1 molar and this is 2S molar. Reaction will take place, suppose X and 2S minus X, then this will be X and this will be X. And since both are OH minus ion, so you will write 2S minus X. So, let us again write both reaction, MgOS2, Mg2 plus 2 OH minus ion, this is S, this is 2S minus X at equilibrium, and you have reaction this NH3 plus H2O, this is your at equilibrium, this is 1 minus X, which is almost equal to 1 molar, and this is your 2S minus X, which is basically OH minus ion concentration, and X. So, we know Ksp will be equal to S into 2S minus X square, and second we know Kb will be equal to your NH4 plus ion So, I am talking about opposite reaction. So, this will be in opposite reaction, this is the product. So, H minus ion by ammonia, and this is your NH4 plus is 1 into H minus is your 2S minus X, 2S minus X by your ammonia is X. So, you have two unknowns Sx, Sx, this is also 2S minus X, and you have a two equation. So, you will be able to get your OH minus ion concentration and value of S, and this value is your solubility of salt, solubility of salt. Precipitation is the basis of wet chemistry. If suppose we want to know the presence of particular ion, what we will look at is if there is any salt of that ion, which is insoluble or sparingly soluble. If we know that a salt of that particular ion is sparingly soluble, then what we do is we will add the counter ion of this particular ion, the particular ion which makes this ion into insoluble salt. And when your insoluble salt is formed, it will precipitate out, and we can know that this particular ion is present. Suppose we have solution and we add Ag plus ion, and we see a precipitate, then we can infer that chloride ion or bromide ion or iodide ion is present. Thanks.